Okay, hi everybody. Happy Wednesday. We're gonna dig in here with a bit of a review from last time, and then we'll move on to elimination reactions of alcohols. If you recall, our theme for this chapter is turning OH into a good leaving group because it is a cruddy leaving group. So we've got a few strategies for doing that. We tried using HCl and HBr, which were okay and would do what we wanted, only we would go through a carbocationic intermediate and therefore get a mixture of products in a 1-to-1 ratio because, of course, the bromine nucleophile could attack from above or below. And what we did there was true for HCl as well. We would get either the chloride or up or the chloride down. And it's expensive to lose stereochemistry. And so we needed some better methods. And so we've got a few that we've dealt with. The first was using PBr3. Recall that this reagent converted the OH into a good leaving group by making a new phosphorus oxygen bond in place of a phosphorus bromine bond. And then the bromide that was liberated after the first step would come in from behind and do an SN2 reaction from the backside to give us the alkyl bromide with inverted stereochemistry. Now, one thing that came up in office hours that I want to point out is you may have been worried about Br- doing SN2 chemistry because we've generally said that good nucleophiles have conjugate acids with pKa's that are greater than 0. And so, that would include things like cyanide and azide, but probably not Br-, whose conjugate acid HBr has a pKa of -9. Nevertheless, experimentally we observe Br-, I- and Cl- are all good nucleophiles. And so that's counterintuitive and against the trend that we have noted so far. The reason they are has to do with their large size and polarizability, which allows them to distort their electron density in such a way that they can really get in there and attack an sp3 hybridized carbon from behind. We won't worry about that reason. I won't ask you why they are good nucleophiles, even though they are such weak bases and so on. But you may need to memorize and/or put them in that category to understand that this reaction can be SN2. As to why the reactions above using HBr go through SN1, whereas this one goes through SN2, I don't know. Possibly water's a better leaving group than this, but I don't have a rationale for it. I can only tell you what is observed experimentally. The second reaction that we introduced had similar results and went through a similar mechanism. Thionyl chloride, or SOCl2, and pyridine give you the chloride with inverted stereochemistry. Another thing that came up in office hours today was whether or not you can use, whether there's cases where you would use one versus the other. Not as far as we're concerned, though there are a lot of practical reasons why you'd use a different reagent for a different context. Some reagents are water or air sensitive, and dealing with them can be challenging. So if you can get away with others that are not, that might be a preference. Some are just more expensive than others, and some work better in molecules that have other functional groups than other reagents. So it's good to have lots of options, but there's no principle I could teach you to tell you when you'd use one versus the other. You can use them interchangeably, but should be responsible for knowing both of them. Oops, why did I do that? Finally, towards the end of last time, we talked about a method of turning OH into a good leaving group without being forced to do this immediate SN2 reaction. For reactions 1 and 2, your first step was turning OH into a good leaving group, and then that was immediately followed by a substitution reaction. But we introduced a new reagent called Paratoluene sulfonyl chloride, and you need a base with this one. That reagent looks like this, which I think I drew for you last time. Toluene stands for a benzene ring with a CH3 group. The sulfonyl chloride is this portion of the molecule. The first step is like the first step of the PBr3 or SOCl2 reactions. That is, we turn oxygen into a good leaving group by making an oxygen-sulfur bond and breaking a sulfur-chlorine bond. Technically, that is a substitution reaction at sulfur, but it may not be useful to think of it as a substitution reaction because the stereochemistry here doesn't change at all. In any case, you get this intermediate with a positive charge on oxygen. Pyridine, your base, that's not a good nucleophile, will then immediately remove the proton, and that gets you to the following structure, which is stable. Okay, and this is the tricky part. This is stable. You can isolate it. You can store it. And then you can use it later in SN2 and or E2 reactions. So, and this is a part that's maybe a little confusing, and you're going to have to memorize it because I don't have a good explanation. Some have asked why, once chloride leaves, do we not have Cl- come in straight away and do SN2? And the answer is I don't know. Sorry, I got nothing. Really don't. And so that may be a detail that you're going to have to memorize. But the useful thing is that you're able to convert OH into a good leaving group without going on and doing another reaction right away, and that allows you to retain stereochemistry at a stereocenter, which, depending on what products you want to end up with, that can be useful. This product is called a tosylate. That is, and the reagent is called tosyl chloride. That's an abbreviation of toluene sulfonyl. And we'll abbreviate it even further by putting a T, capital T, lowercase s by the O to indicate that all of this is there. Okay, so you need to be used to seeing that abbreviation. Organic chemists are notorious for that kind of thing, and after a while it becomes a bit of alphabet soup, which gets annoying. We'll try not to do that as much as we can. But in this case, since we don't want to be drawing all of that stuff every time, it's fun just to simplify. So why might you do this? Well, suppose you had a starting material like this, and you wanted to end up with the following product. Sorry. Yeah, the following, oh, well, hold on. Last time we talked about a similar situation to this where you wanted to replace the OH group with something else, and you couldn't do it directly, first because the OH is a terrible leaving group, and secondly, because a single SN2 reaction would result in the Cn minus being down. So what you can do instead is two tandem SN2 reactions. Use PBr3 to first convert the OH into the inverted bromide, and then in a subsequent step add your nucleophile, and that gives you the right stereochemistry, which works fine. And then the question is, if you wanted to use the same starting material, but instead get to having replaced the OH group with Cn, but now have the stereochemistry be down, the side step or the workaround is first use Paratoluene sulfonyl chloride with pyridine as a base to convert OH into the tosylate without changing stereochemistry, and then in a subsequent step you add Cn minus and you do the SN2 reaction. So the key is that the tosylate works without inversion of stereochemistry. All right, so that's 3 new substitution reactions. And we've talked a lot about strategy and the reasons why these things occur, but nothing is going to save you from forgetting what on earth a reagent does. So you may need to memorize some of these things because, as I said, there are a lot of why questions here that I simply don't have the answer for. So in dealing with reactions and preparing to design new molecules and propose syntheses, it can be useful to think of each new reaction in 3 different ways. First is, if you're given a starting material and a reagent, could you predict the product? Second, if you were given a starting material and a product, could you identify the reagent that could make that happen? And third, if you were given a product and a reagent, could you identify what the starting material would have to have been? You can make yourself flashcards or write things down on a sheet of paper, but if you do that and practice it for each new reaction, it will be much easier for you to answer questions where they ask you, convert molecule A into molecule B, using any of the reactions you know how to do. All right, questions so far? No? All right. So now we're going to talk about elimination reactions of alcohols. And again, the strategy is going to be convert OH into a good leaving group and then do elimination. We're going to have 2 basic strategies. One's going to be an E1 type pathway and the other is going to be E2. The E1 type pathway will have a carbocationic intermediate, and that's going to introduce some challenges for us. The E2 reaction will have no carbocationic intermediate and will sidestep some of the challenges of the E1 approach. All right, the E1 approach is the simplest one because it follows a strategy that makes the most sense. So you use a catalytic amount of sulfuric acid, and I will point out that whenever you're using sulfuric acid, water is probably the solvent. The pKa of sulfuric acid is like -11. If you're in water, that means that 100% of your sulfuric acid is actually H3O+, and then the conjugate base of sulfuric acid called bisulfate. That's not a critical issue, and so I've chosen to stick with the mechanism that your text shows, where I think sulfuric acid does the work. But you can also do this with other acids that include hydronium. So the first step is simple acid-base chemistry, where we protonate the alcohol, thereby turning it into a good leaving group. It can leave as neutral water. The next step is leaving group leaves to give us a carbocation. So far, this should look exactly like an E1 reaction or an SN1 reaction. The only different thing is that we had to protonate the OH group first. So here's your carbocationic intermediate. Water just left. Of course, water could hop back on there, and if it did, that would just be going backwards. Some have asked at this point, why doesn't the bisulfate ion hop on there to give you a substitution product? And there's some evidence that that does occur, but that it is not a particularly stable product. And so you don't need to worry about what I just drew, okay? Does that attack happen? Probably, but the product isn't that stable, and so that it would go back to the carbocation, and in particular, if there are other steps that lead to more stable products, we would never get that much of this. So I'm going to erase that so you don't feel like you have to memorize it or accept it as a possibility. Here's an alpha carbon, here's a beta carbon, there's a beta proton. You can use bisulfate or water as a base to remove the beta proton and generate the new alkene or olefin. Notice you also regenerate sulfuric acid or H3O+, which is how you know that you only need that as a catalyst. Overall, this process converts the OH group, exchanges the OH group for the olefin. All right, so it's an elimination reaction because the leaving group leaves and then we remove a beta proton. Question so far? For most of the reactions that we've dealt with so far, we have sort of assumed that they went pretty downhill in energy. For this reaction, the equilibrium constant is pretty close to 1, which means you could actually start with the olefin and add catalytic acid, and you could go backwards to get the alcohol. And in fact, that is a chapter 10 reaction. I'm telling you about it now so that when we get to chapter 10, you don't say, hey, wait a minute. Didn't we just do the other way? What the heck are you trying to pull? The answer is that you can go forward or backwards here. And when equilibrium constant is close to 1, we have to take other experimental steps to isolate a desired product. One interesting feature of olefins is that they have lower boiling point than alcohols do. That's because they lack the hydrogen bonding capability of alcohols. And so you can actually distill off the olefin to drive the reaction to completion. This is an example of Le Chatelier's principle. If you remove the olefin from the equilibrium, the backwards rate slows down and the forward rate can win. In contrast, we'll see if you have the olefin and you want to end up with the alcohol, you just need to add an excess of water. Okay, so that's okay. That's not such a big stretch, but we need to talk about a problem that happens with carbocation intermediates. And this, as I told the earlier group, is probably going to be pulling back the curtain on a horror show that you didn't want to know about, but is nonetheless happening, and so now we're going to know about it and worry about it. Before we do, though, I asked the earlier class for some help with some terms I'm hearing around home that I'm hoping you can shed some light on. One of the more recent one is let's go, but it doesn't refer to actually going anywhere. Have any of you heard of this usage? So context.
Yes.
Yes, yeah. Context is that a kid on a scooter will do some awesome trick and he lands it and then says, "Let's go!" Let's go where? Or Adam, the youngest, will hear, "Oh, we're going to go get ice cream. Let's go!" Well, that makes sense, actually. In that context, it makes sense. Anyway, so okay. In that case, let's go is a celebratory exclamation, and one should not infer an imperative. Is that?
Correct.
Okay, all right. The other one was sending it, to send, or also full send, as opposed to half send, I guess. I don't know. And that's encouragement to do something dangerous and stupid. Is that? Or do something hard? Okay. And then there's another one that I've struggled with, which is yeet. Which earlier, again, Hannah, I'm sorry, this is old material, but we tried to conjugate it to yeet, as it is in the infinitive. I yeet, you yeet, he, she, it yeets.
Thou yeeteth.
Thou yeeteth. Thou yeeteth. You sure? I feel like it's like the scene from The Office where Dwight and Aaron are working on Dothraki. I throat rip. You throat rip. He, she, it throat rips. No? We yeet. You, plural, ye, yeet. Y'all or they yeet. The leaving group yeets. Yeets. So, and then you can have some fun with like past tense, I yeeted, or perhaps I yote, or what hast thou yacht? Anyway, and then they were, yeah. Doctrine and Covenants 66, inasmuch as you can send. Wow, hey, that's good. And then somebody else was saying, and thus the devil cheateth their souls and carefully yeeteth them down to hell, or something like that. We learned that yeet was also a celebratory exclamation, often involved when throwing something or dancing. Or doing something else dangerous? I don't know. So, maybe it'll be in the new hymn book. If you chanced to yeet a frown. No. Okay, well, we need to think of some more. But thank you for that little lesson. Right. Carbocations. Now is the less fun stuff. Actually, I think it's awesome. So do you remember how I told you primary carbocations are very unstable? They're not really great intermediates. It turns out the structure of a primary carbocation has been somewhat controversial in organic chemistry. And even though they're not good intermediates in solution, they can exist in the gas phase, in outer space, in vacuums. And so some have tried to sort of use calculations, since they're trouble to observe directly, to use calculations to try to figure out what's going on with the carbocation. And our picture of carbocations so far has had a positive charge on what we've called the alpha carbon. And then on the adjacent carbon, we've said hyperconjugation can happen, where we allow the filled carbon-hydrogen sigma bond to interact with and mix with the empty p orbital. We've called that hyperconjugation. And the new sigma plus p orbital looks like, almost like a partial pi bond. It looks like a CH bond that's sort of wanting to lean over and maybe become something of a pi bond. Okay. So I did some calculations over the summer while I was studying for this class I was going to teach in the fall, trying to verify something I read in the book, because I had just recently bought this computational program suite and wanted to test it out. So if you give this structure as the starting point for some calculations, you put it in the gas phase, that is by itself in a vacuum, and you tell the program, optimize the structure, move atoms around to get the lowest possible energy, what you get as an output there is not that structure that we started with. Instead, you have an intermediate structure which has the hydrogen, and we could maybe number these carbons, I don't know, 1 and 2. It has the hydrogen evenly shared between 1 and 2 with partial bonds, partial sigma bonds between carbons and hydrogen, partial pi bond between carbons, a positive charge delocalized among all three. This structure has a hydrogen that's sort of bonded to two things, and so it's called a hypervalent hydrogen. And they actually call this, instead of a carbocation, they call this a carbonium ion. And it's unusual because you've got 3 atoms with only 2 electrons shared between them. That's why they're dotted lines there instead of actual lines. I suppose if you wanted, we could draw 3 resonance structures, one with a single line here, the other with a single line there, and another with a single line there. It's the hybrid of those 3 isolated structures. And if you try to calculate what the orbital looks like that corresponds to the carbon-hydrogen bond in our starting structure, what it looks like is really kind of cool. It looks like a pi orbital that just happens to envelop that hydrogen. And so what you've got for this carbonium ion, which actually is, it's still high in energy, but it's at a minimum, it's an intermediate. It's what you would get if the hydrogen started leaning over and sort of stopped halfway through, okay? And there's been debate in the organic chemistry community as to whether this starting material, whether the regular carbocation is the energy minimum or a maximum versus the carbonium ion. Carbocation, TS versus transition state versus intermediate, that's the same as maximum versus minimum, and so on. And it's been fairly controversial. Calculations have suggested that at least in the gas phase, it's the carbonium ion that's the lowest energy structure, which means we now need to start thinking of carbocations a little differently. And we can ask the question, what if that hydrogen just continued to lean on over, keeps leaning, just like Joe Fusco Jr. in the Christmas classic While You Were Sleeping. I endorsed it last time and hardly anybody knew what it was, so I'm just going to let it go without further commentary. If that hydrogen continued to lean on over, we would eventually get to a situation where the CH bond was on carbon 1 instead of on carbon 2. We traded. We moved atoms around. We rearranged from one carbocation to another. And in fact, this process happens all the time with carbocations. CH bonds and even carbon-carbon bonds on beta carbons, that is, the carbons that are adjacent to alpha carbons, can lean over, pass through the carbonium either intermediate or transition state, and then become rearranged. So this can happen all the time with carbocations, which is another reason why generally you want to avoid using carbocations when possible. Nevertheless, we want to at least start to anticipate this possibility and use it where we can to explain experimental observations. So earlier in the first hour, one student asked, how do we know that the reaction is E1? How do we know that bisulfate doesn't come in at this earlier step and do an E2 reaction? That's a great question. You wouldn't know that, actually, from this particular example. But there's an interesting experimental result that you can only explain if there's a carbocationic intermediate. So I want to show you that interesting experimental result. Before I do, though, any questions about this carbocation rearrangement? Go ahead.
Does it make a difference if it's secondary or tertiary?
Does it make a difference if it's secondary or tertiary? Yes. So you've noticed that both of these carbocations are primary, so, and they're actually the same. So it's the rearrangement is sort of a non-issue here. But you want to especially pay attention to the possibility for carbocation rearrangement when it allows you to shift from a less stable carbocation to a more stable one. And we'll see an example of that in just a second. Can it happen with groups other than hydrogen? Yes. When it happens with hydrogen, we call this rearrangement process a 1,2 hydride shift because hydrogen's moving with its electrons. If it happens with a methyl group, we could call it a 1,2 methyl shift, and I'll show you an example of that. Braden from the chat just proposed the song "If You Could Yeet to Kolob," which is kind of, that could work. I'm not sure that one's making it into the new hymn book. I personally really like that song, but it's on the weirder side of songs that we display before the public, so I just sort of wonder whether that one's going to make it. Back in Wisconsin, when I was at grad school, I was the ward organist. I've sort of done that. Once you're an organist and people know about it, it's hard to make them forget. That's sort of a bell you can't unring. And I knew that our bishop's wife hated that song. And so there was one Sunday where the meeting was over, playing the postlude, and she was sitting right in front of Amber and our little guys. And I looked over at her, made eye contact, and then started playing "If You Could Hie to Kolob." And it was kind of fun. She shouted at me from across the chapel, and that was probably not as reverent as it should have been. But, there was a guy in our ward when I was really young, and I never actually heard this, but he was alleged to have gently worked in the Cougar Fight song into his prelude at various times. I've never attempted that. The one thing I did, I think I showed up early on a Sunday, and there was nobody there except the guys setting up chairs, some of my fellow elders, and so I used the pedals to play the Seven Nation Army, and then I stopped before I got in trouble. All right, so here's a situation where you get carbocation rearrangements. Use catalytic H2SO4. You would predict going through the following intermediate with a positive charge on a secondary carbon. You would predict in E1 style, there's only one kind of beta proton here. The other beta carbon just has methyl groups on it. So you would predict the only elimination product could be this one. And you do observe that, but we also unexpectedly see the following. Now, if you count carbons, we've got the same number of carbons, same number of hydrogens. These are isomers, but they're connected in totally different ways. And the only way you can explain this, actually, is if you allow a methyl group on the other beta carbon to lean over, go through a carbonium ion transition state or intermediate, and then continue leaning over to make a rearranged carbocation. Let me try to show you how this would look. I'm not going to draw the orbitals this time. So here's your secondary carbocation. Here's alpha carbon. This is a beta carbon. The CH3 can start leaning over until you would pass through an intermediate that looked kind of like this, where a carbon is somewhat evenly shared between our alpha and beta carbons. For the sake of our discussion, we'll call this carbons 1 and 2. Partial pi bond character here, positive charge, and then it continues to lean. Here's our carbonium ion. It may be a transition state, it may be an intermediate. Keeps leaning. And then completely forms a bond with carbon 1, leaving carbon 2. Oh, I don't like my penmanship there. Leaving carbon 2 with the positive charge. And if we were to draw orbitals, they would look very similar to what I showed you above. In a mechanism point, from a mechanistic standpoint, the way you show an arrow pushing mechanism for carbocation rearrangement is quite simple. You simply take this line and draw an arrow towards the positive charge. This is an example of a 1,2 methyl shift. Now, this process is an equilibrium process. It can go backwards and forwards, but the equilibrium constant is greater than 1. Can you tell me why the rearranged product carbocation might be preferred relative to the starting carbocation? Yeah, go ahead.
Just because it moves it on a tertiary carbon rather than a primary carbon?
Right. The positive charge is on a tertiary carbon. Those are more stable because of more hyperconjugation opportunities. So when you have a carbocation with groups on the adjacent beta carbons that, if they moved over, would leave behind a more stable carbocation, then rearrangement can occur. Here's one of those patterns: a secondary carbocation adjacent to a quaternary carbon. That is a carbon bonded to 4 other carbons. That's one of the cases where carbocation rearrangement can occur. If we now draw this carbocation from a slightly different point of view, you can see where the other elimination products come from. And actually, I'm going to use color. If we remove either of those identical beta protons, we're going to get this product. And if we remove this beta proton, we're going to get the more substituted alkene product. We'll call these rearranged products, and we'll call this an not rearranged product. And I would expect you to draw all 3 as products of this reaction. I would not expect you to say whether the rearranged versus the non-rearranged dominated. Sometimes your text, though, will give you a problem and show you one or two of the rearranged products and as the only products, and then ask you how it happened. But for my predict products questions where carbocation rearrangement is a thing, I want you to draw all the possible products, rearranged and not rearranged. I won't expect you to tell me whether rearranged dominate over not rearranged. Okay, questions so far? All right. So another situation where this could occur would be if you had, say, a tertiary carbon adjacent to a secondary carbocation. Then, via a 1,2 hydride shift, you could go from a less stable secondary carbocation to a more stable tertiary carbocation. So that's when you want to pay attention. Tertiary carbon adjacent to secondary carbocation, or quaternary carbon adjacent to secondary carbocation. So why did we bother with this? Two reasons. First, to highlight the usefulness of a process that doesn't have a carbocation rearrangement. I will just briefly mention that process now, and then we'll deal with the mechanism some other time. But the E2 strategy can use this same starting material, but use phosphorus oxychloride, POCl3. Many students memorize that as POCL, which sounds maybe, I don't know what it sounds like. I was going to say a Pokemon, but that's probably just because of the POC sound. So I withdraw the suggestion. You get this only and no rearranged products because you don't go through a carbocation. The mechanism for that's in the text, and we can discuss it next time. You can look it up. It's very similar to what we have done previously. Go ahead.
There's a question in the chat.
Are carbonium ions similar to resonance structures in a way? Well, let's look at it this way with the simple drawing. Anytime you move atoms, it's not a resonance structure. So this carbocation and the rearranged ones are in equilibrium with each other, and they too are in equilibrium with the carbonium ion. You're moving an atom, so resonance doesn't apply. However, if you look at that carbonium ion structure, it would be probably okay, though a little weird, to draw three resonance structures for it. One in which you have a positive charge here, one, and you keep all the atoms in the same place. One in which you have the positive charge on the other carbon, and perhaps another like this. And again, you don't have ideal geometries for any of these bonds, but you could think about these as being resonance structures of each other, as long as you don't move atoms. The carbonium ion is a so-called 3-atom, 2-electron bond. It's not a conventional bond. It's difficult to draw with Lewis structures. But interestingly enough, you tell the program to optimize that carbocation structure, and that's what it spits back out at you, which is sort of just kind of cool and kind of bizarre. All right, other questions? So the second reason I told you about this is that I wanted to create the foundation for understanding something really cool that happens in cholesterol biosynthesis. And I'm going to try to find the last time I talked about that so that I can show you. This will be notes from another class, and what I'm going to show you, you really don't need to memorize. Can I even find it? Let's search everything for... Ah, there we are. Oh, there's some even weirder carbocations that you don't want to know about. Okay. So the process of cholesterol biosynthesis involves getting from a carbocation on this faraway structure to a carbocation on a tertiary carbon several bonds away. There's a lot going on there. Don't worry about it. Cholesterol has this fused 6-membered ring structure. I've seen that before. With another one here and then a 4-membered ring. Incidentally, all of that comes together in a great cascade of reactions involving pi bonds, positive charges, and epoxides. We'll be able to understand all of that by the end of the semester. But what happens in order to get the carbocation to move that far away, what has to happen is a series of rearrangements, right? So the blue proton leans over. See if we can show that process happening. Leans over, you get the bridged carbonium, either transition state or intermediate, and then it ends up on the other carbon, which leaves a positive charge on carbon 18. And then the orange proton does the same thing. It leans over, bridged carbonium intermediate, and you make a new bond with 18. Now you got a positive charge on 14. And notice that in both of these cases, we're trading tertiary carbocations for other tertiary carbocations. So you might not expect it to be downhill, but you can promote, perhaps the enzyme promotes the desired carbocation with its active site and with the fact that you can eliminate from the final carbocation. Now you're at a tertiary carbon that's adjacent to a quaternary one. So CH3, which was hyperconjugating with that positive charge anyway, leans over, bridged carbonium intermediate or transition state, and ends up there with a positive charge here. If you look at where we need that carbocation to be, it's atom 10. We're almost there. Finally, the down CH3 on carbon 10 leans over, goes through the bridged carbonium intermediate and makes a new bond with 15. That leaves the positive charge on 10, and at that point we do the E1 reaction. That gets you the double bond in the right place. That's a cascade of 1-2 carbocation rearrangements. I can't remember how many of them we did. 1, 2, 3, 4. 4 different carbocation rearrangements that allow us to get to this product, linosterol. And this is a precursor for all the steroid hormones and all cholesterol and bile salts. It takes 19 more steps to get to cholesterol. And then some other steps beyond that to get to estradiol and testosterone. But this kind of stuff's going on inside you all the time. So even though we've pulled back the curtain on the horrible, horrible world of carbocation rearrangement, it was going on inside of you all along and you didn't know. So now you won't be able to sleep at night thinking about all the horrible carbocation rearrangements that are happening inside of you. But hopefully you can see some of the beauty and logic of these things. The stereochemistry of these 1-2 rearrangements is really cool. You start at, everything ends up on the same side as it was to begin with. Things just lean over, and there you go. There's the new bond. So do not memorize that. Do not stress about it. But it's an interesting demonstration of carbocation rearrangement. All right, I will see you next time.